Okay, cool.
Okay, yeah, so for our last talk today, we'll have Mateo S Zhang, who's finishing up his PhD at Toronto and will be starting in the fall as a postdoc at MIT. And he'll be telling us about midpoint methods for SDEs.
Yeah, so thanks Austin, and thanks organizers for inviting me to this wonderful conference. I also thank all of you for sticking around till 5:30. But I'll try to keep you a little bit entertained. So this is based on joint work with myself and numerous collaborators. So there's Jason over at Penn, Nick, who is right there, Sitan at Harvard, Sinho at Yale, and then Stephen and Jerry, who are PhD students of Nick over at CMU. So I'll just quickly mention, this has kind of been beaten to death, but these kind of SDEs for generative modeling appear all over the place, whether it's for like MCMC or posterior sampling. You find them a lot in scientific computing. They've also shown up in the guise of these diffusion models, which have been used for weather, biomedicine, generative models. OpenAI released a new image model, I think 2 days ago, that relies on these type of diffusion equations. So really, the type of thing that I'm going to treat in this talk is going to be a rather general formalism that kind of has broad, kind of ubiquitous usage across different fields of modern machine learning. So without further ado, I'll kind of boil this down to a paradigm that to me captures the essence of a lot of these applications, which is, we want to simulate a stochastic process, leave it in this abstract form, and then apply this to various ML tasks. So this is, kind of a very simple generic stochastic process, which says that, I have a particle, it moves according to some vector field. This field can be inhomogeneous, so it depends on time. And then it's kind of kicked around by a Brownian motion. So what sort of examples does this admit? The kind of simple one, maybe I should move this guy. The kind of most simple example that this admits is, where I'm personally most familiar with is these kind of sampling MCMC type applications where you have a static vector field. In particular, if you assume this as a form of a gradient field, it's a gradient of some potential V. Then, under relatively mild conditions, this admits a stationary measure which is proportional to the exponent of minus v. And in this case, or in general, we have some notion of an oracle. So this is, if we want to implement these on a computer, there's a certain object that we have to query in order to, really implement this. So in the case of Langevin diffusion, you may have access to gradients of the potential. You might also have access to the value of the potential itself. And you kind of want to, through queries to this, simulate the equation given by these dynamics that I've written above. Okay. Another and increasingly more popular application is these DDPM or diffusion-based generative models. So one particular paradigm of these is that you have X, and then it moves, again, according to a simple SDE, but this time with an inhomogeneous vector field. The vector field depends on time. In particular, the type of application you see for this has kind of been discussed before. You start from some noisy distribution, and then this vector field is supposed to help you move from noise back to informative data samples. So here the oracle would be like, I've trained some neural network to learn this magical vector field hat S. And then, how many times do I have to query this neural network in order to actually simulate this equation? And the kind of computational primitive that we want to understand in all of these cases is how do we simulate an SDE accurately using as few calls to the oracle as possible. So you can imagine in either of these cases, the oracle is something that is expensive. If you're a user that actually cares about computational cost, then it matters to you how many times you call this oracle. And if I can reduce a number of calls, then I'm happy. I can save resources, or I can have more ChatGPT models running at the same time. Cool. So for this talk, I'll start with a warm-up, which is, if I have an ODE and there's no noise, you just have a particle following some vector field, how do we simulate this guy? So in general, there's no closed solution. You can't integrate this to get anything that you can really implement on the computer. So the question is how do I simulate this? And a simple way is to do these Euler discretizations, which just says given some starting point, I push forward my vector field, I query it at the initial time, and then I kind of take a small linear step. So this is known as like the Euler method. It's kind of very canonical. You know, it's very simple to come up with more sophisticated methods. The simplest one would be like a midpoint method. So I take my initial point, I run an Euler step. It turns out that if I run this Euler step for half my step size, then I can use this point, put it back in the vector field, and then obtain the actual iterate. And this is known as a midpoint method because I've queried one midpoint, which is kind of somehow in between my initial starting point and then the point where I've ended up. And for ODEs, there's a very classical theory that says that like under some generic assumptions, these midpoint methods do better. And in fact, you can cook up all sorts of complicated methods that do arbitrarily well given some strong set of smoothness assumptions. Okay. So the question is, what do we do for SDEs? So really, like on its surface, the equation doesn't differ by too much. And so a natural generalization would be to run the Euler step on these dynamics. So here, if I want to discretize the Brownian motion, what that really corresponds to is I have like some random vector xi, which is drawn from an IID Gaussian. I scale it by an appropriate amount, and then I follow the kind of linearized dynamics for a small step. Okay. We can very naturally formulate a midpoint version of these dynamics, and in fact, this was done quite long ago in the literature. In fact, you can make this midpoint random. So I take some step, you can imagine I have this variable u, which quantifies like how far of a midpoint step I want to take. Lives in 0, 1, it's sampled from some distribution p. If p is deterministic, let's say like it's a delta mass at 1/2, then this is kind of looking like the midpoint method for ODEs that I showed on the previous slide. And then, what I do is I push forward, I have my first equation where I push forward some kind of linear step for a small step size. And then I put this back into the vector field, so I query the vector field again, and then I push forward this for the whole time. And you can kind of view these Gaussian random variables, they're correlated, which is important, but they kind of are just like realizations of the Brownian motion. The key point is that they're correlated. Okay, great. And so the kind of punchline or the thesis of this talk is that these midpoint methods significantly save oracle queries. I guess this is not particularly surprising. This is sort of what we would expect. The nice thing is, we have a good kind of theoretical characterization of how much they expect, like you would expect to save in terms of query complexities, both for MCMC and for these diffusion models. The interesting thing for me, because I'm kind of like a troglodyte when it comes to like implementing stuff in practice, is that somehow, this was implemented in practice, and it actually does seem to do well. This is, very cool for me, which is like I'm used to running simulations on like 2D Gaussians or something like this. So to see this actually do better in a setting that people care about, for me, that's pretty interesting. Okay. So I'll start by like kind of an extended warm-up, which is really these midpoint methods for MCMC, and then talk a little bit about where the theory has advanced to in the last couple years. So in general here, just kind of recapitulate the formalism. We want to sample from a Gibbs measure, so pi proportional to exponent of -v, and we assume that the potential is well conditioned. So there's kind of upper and lower values on the Hessian that hold uniformly in space. Cool. So the standard approach, like I've said, is the Langevin diffusion. This is a very simple homogeneous SDE, which corresponds to like you have the vector field being a gradient field for some potential v. There's also better variants that we study in our work, which is on these underdamped Langevin diffusions and also Hamiltonian dynamics. I think for the purposes of this talk, it's not really instructive that I give you the precise formulations of this, but it's good to know that there are a family of such methods that exist, and the analysis gets increasingly tricky as you kind of make these methods more complicated. Okay. So the canonical method for discretizing these using randomized midpoint, this was invented by Yin-Tat Li and his student Ruoqi Shen over in 2019. So what this does is, it kind of instantiates the method that I've wrote more in abstract terms in the previous slide. So you kind of query a random midpoint, using this variable un, which lives uniformly on the interval. And then you use this midpoint in the vector field. Here the vector field is homogeneous in time, so we don't need to worry about like where we take this v. This v is constant in time. And so it's a very simple method. So you take one midpoint, then you run these dynamics. So the question might be asked, like, why do we expect this to help? Like, formally, it's good to understand like why this expects to do better. And so when we actually integrate over this random variable u of n, essentially, like when you integrate this gradient term here, you're going to see that compared to the Euler step, which kind of is always taking the gradient to be at some fixed time nh, here you instead have an integral of a vector field evaluated at some other process which is given by the midpoint, which is xt plus. And so if you actually step through the error analysis, you note that this kind of process is actually a lot more similar to the continuous time process, and we can quantify why. So if we go to the next slide, in general, if I have n IID random variables, it's pretty simple to see that the expected norm of their sum, under some benign conditions, is going to scale on n, the number of random variables, times their mean, plus the square root of n times the variance. This is a very simple like CLT type argument. But what does this mean for stochastic processes? So if I have an ideal process and it produces a happy variable x, and then I have some like lame process that's producing a variable x hat, then the weak error we can define as being corresponding to the bias or the mean of the random variables, which is like how much the process would deviate if I take their expectations, right? So this is kind of a difference in means. And I can also control the variance or some notion of it, which is like how much the processes differ in L2. And so in general, there's a very successful line of literature which says that we expect the n-step error to be to scale as n times the weak error plus n square root of n times the strong error. And this is really not so much more different than this kind of very generic intuition about IID random variables. And this is opposed to like if I didn't separate between the weak and strong errors, but I only looked at like one step L2 control, then I would expect something like n times the strong error if I didn't account for like any type of weak error at all. Great. So for this overdamped randomized midpoint, it's not so difficult to analyze this, and when you take the number of iterations to be like 1 over the step size, you can show that the weak error is scaling as d dimension square root times h to the 5 over 2, and the strong error is scaling as this, but minus 1 factor of h. And if you plug this into the formula, and your desiderata is that you want the measure of a stochastic process to be less than epsilon, then you would expect the number of iterations you take. Well, you have to pick h here so that this is less than epsilon. And then you invert this to get n. So you get this d to the 1/2 over epsilon. And this just comes from like dividing the strong error by square root of n, or square root of h. In comparison, for the standard like Euler method, here there's no separation between the weak and strong error. So if you take this and you put it into the weak error and then you divide by h, then you're going to get like d to the 1/2 h to the 1/2, and it's some simple algebra to show that this requires d over epsilon squared number of queries. So the key takeaway from all this kind of abstract machinery is that if I pick a midpoint, and in particular if I randomize in this way, I'm actually reducing the bias of the scheme. And I'm doing this in a way that's not introducing like too much variance. So somehow, this is a very nice like canonical scheme, and in fact, there's some literature from Jianfeng Liu and collaborators that shows that this is actually order optimal in terms of discretizations for Langevin. Cool. So moving on, this is now my own research. So this kind of recent work shows that if I discretize the underdamped Langevin, which is somehow a better method in some notion, and under the standard assumptions, we can actually output a measure which has bounded error in a kind of nice way. So there's a couple of things to know here. This is d to the 1/3 over epsilon to the 2 over 3. This is kind of like an expected rate for people who have worked in sampling. This was a kind of targeted. This was a rate that people had wanted to get for a long time. The interesting thing here is that this is kappa to the 5 over 6. So this was the first result that really managed to get anything that's sublinear in kappa. Somehow in optimization for these underdamped dynamics, we expect these square root kappa rates to follow from some fairly elementary analysis. In sampling, it's been really a large open problem to try to push this anywhere to sublinear. So I'm happy with this being the first sublinear result. Clearly, there's still a gap between this and like any type of square root kappa. And then a recent follow-up paper from this year shows that for a related scheme that works for Hamiltonian Monte Carlo, you actually can get even better dimension dependence and polylogarithmic dependence on epsilon. So instead of having this polynomial power, you have like log squared or something like that. This requires an additional smoothness assumption. So you need the Hessian to be Frobenius smooth with some constant beta h. So there's some scaling in beta h here that I've not made explicit. Okay, so all of this is like pretty straightforward intuitions. You might ask like, why do we need you, Matthew, to do this research? Why don't we just put this stuff into ChatGPT? So there actually are some interesting ideas, which I'll go through like pretty quickly. But at a high level, usually we analyze these type of midpoint discretizations with coupling. This is a very natural way to see the separation between weak and strong errors. Unfortunately for these accelerated underdamped dynamics, the type of stuff that we did in the previous two papers, the system is not contractive. And as well, there's kind of other barriers to doing these things purely using coupling analyses. So the idea that we came up with that was pioneered by my two collaborators and extended by me, which was instead of having the error accumulating exponentially fast, is to somehow take these coupling arguments and slot them into like an entropic or a Renyi divergence argument. And this, I guess, is a very kind of deeply technical point, which is not very easy to explain. But somehow if you do this and you put the coupling arguments in the right way, you don't get this exponential error, you only get a kind of linear accumulation. And this is sufficient to get the side of the kind of rates that I obtained in the previous slide. So there's a very high level idea here, which is like to introduce an auxiliary process whose error is bounded using Girsanov and other techniques. I don't have time to really get into this, but this occupies the majority of the paper. Okay, I'll tell you a little bit about diffusion models. Okay, without kind of spending too much time on the formalism, there's some process that runs a type of SDE. It turns your lovely Gaussian noise into tacos. It kind of does this by assuming that you have access to some nice vector field S of t, which, the formalism, I won't really get into the weeds here. But the idea here is this idealized vector field S of t. You can kind of approximate this well with neural networks via some black magic up to some error. This is kind of score estimation techniques. It's, I guess, been talked about by other folks in this conference. But, this is the sort of onsets that we operate under, is that we have some system which is like inhomogeneous time in terms of the vector field that we want to simulate. And if we do this, then we can, generate samples from like any kind of nice distribution that we want. Okay, so the problem is, you have access to this trained vector field ST, and then how many times do we need to evaluate it to get a reasonable sample? And so for these SDE-based methods, there have been rates obtained, and these are usually for like Euler type discretizations, and typically the rates scale linearly in dimension. So there's many citations here. I've chosen this one by Giovanni Conforti, Alan Dermas, and others, but there's a whole slew of works analyzing these, showing various types of guarantees. The question we posed was, can this be improved by midpoints? And so that's, I'm going to tell you a little bit about this. So, we introduce a randomized midpoint discretization. Okay, it's a little bit complicated, but like the key difference between Langevin is that because we have an inhomogeneous vector field, we need to be careful like the time that we evaluate it. So other than that, like it's pretty much the same, like we have a uniform distribution over the midpoint time. And then we do kind of like a midpoint step. You just need to be more careful with like where you're indexing the vector field in time. So this should help in a similar way as it does for Langevin dynamics. Okay, without getting too much into like what happened in this paper, the analysis it does get a little bit complicated. So in general, for these vector fields, you don't expect kind of uniform Lipschitz bounds in time. Instead, you have some Lipschitz parameter that varies in time. And so like usually when you have stuff like this, the way to deal with it is you might have like some time varying step size schedule that kind of takes into account, if you're really like have a terrible Lipschitz constant at some point in time, you should take small step sizes. If you have good Lipschitz constants, you should take larger step sizes. And of course, you also have to account for the fact that like you're running dynamics according to some kind of learned score, but this is only an approximate quantity for the actual score. So you need to fit this into the analysis as well. Okay, we did this. It was a bit of work, but nothing too crazy. And so we eventually get to this theorem, which shows that if you satisfy some kind of smoothness assumption and you have L2 estimation, then we can get a sample in some metric which calls this learned vector field a number of times that scales as d to the 1/2. So this is scaling sublinearly in the dimension. Of course, we have to impose some additional smoothness assumption, but our intuition is that this is a kind of mild assumption and not something that's too awful. We verified in a couple examples, and then the interesting thing that I'm about to show you is that we ran this in practice and it just seems to work. So these assumptions are either like fictitious or don't manifest like in the worst case on like most examples that you'll see in the wild. I'll mention that this is the first sublinear in D result for these type of SD methods. There is a concurrent work that claims a similar rate, but we're using very different techniques. This is from Gen Lee and collaborators. Cool. So Nick had several of his students and himself. So somehow they ran experiments. I don't really know. I'm like Neolithic in terms of like my technology, but it shows that the method does better. Like the green is us, and then there's kind of various competitors that they analyzed. And the cool thing is they made pictures. So this is like pretty interesting for me. I don't know if there's like a visible difference, but for me, like, if you squint, the midpoint method, I think it does better than the Euler method. I'll leave that for you to judge. If you want something quantitative, you can go back to the previous slide where I had like numbers. But, I claim that it looks better. Maybe we should do this like double blind and you guys can have a vote, but it seems to me that like there's less artifacting around some of these things, the backgrounds of CRISPR. I don't really know what people are looking for here, but for me, I'm very happy just to have any kind of pictures at all. So, yeah, so that's basically it. So, a lot of future directions. I've listed a couple of them, which is like, can you leverage some structure of the data in this diffusion model setting or in the Langevin setting? With these like midpoints or any type of discretization, and can you apply this to kind of other families of SDEs, things that are not falling in the paradigms that I've discussed, or stochastic processes that aren't SDEs. So this is like PDMPs, Poisson type processes. You can kind of cook up like whatever. But the punchline, at least in this talk, is that midpoints save Oracle queries, both provably and apparently in practice as well. So thank you for your attention, and hope you enjoyed the talk. Thank you.
Okay, so we have plenty of time for questions.
Correct. Yeah. Yeah, so the friction coefficient we choose in this setting is we choose gamma to be square root of alpha. And then it just kind of like, with this choice, we absorb it into the parameters here. But this is kind of a key point that, so here, like when you want to go fast, the system is not point-wise contractive, right? So here you have some kind of like relaxation that kicks in after some time. And so this is the reason why we like needed to introduce a bunch of machinery in this paper. But yeah. 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 We don't assume that you know like the whole Hessian. We just assume you know like some lower bound on the eigenvalue, and then like the result you get is going to be like dependent in terms of the lower bound on the eigenvalues of the Hessian. Like we don't assume that you have like access to the Hessian at every queried point. So like this is only in terms of like I give you some potential. You suppose that there is some lower bound on the Hessian, you get some bound in terms of this lower bound on the Hessian. You don't assume like oracle access to the Hessian. Yeah, so this thing down here, this is for like some type of HMC splitting. This one is for like this is for some type of SDE, so it's not like these Hamiltonian dynamics where you can kind of split the noise from like you can have like injecting noise and then like momentum refresh and then run like ODE and then momentum refresh. This one is kind of, this is a SDE where like it's possible to split, but we didn't consider that in this work. Yeah. But the second one is for some HMC with a splitting. So we actually, this is not really in my slides, but there's some splitting that we do for these Hamiltonian dynamics. It's a little bit convoluted, but yeah.
correction term, you have Milstein scheme. Have you tried to use that technique? Because usually Milstein have a lower error.
Yeah, I'm actually not sure how this compares to Milstein's schemes. There's all these other types of schemes as well, which assume that you have access to like iterated Brownian integrals and things like this. So in our case, we just assume like, as far as I know, this is the most competitive rate. I haven't deeply considered the comparison against Milstein's scheme.
The thing is that Milstein is really easy to implement, so probably it's analytically could be easily handled by the
Okay.
techniques that you propose.
Yeah, it's possible.
So, this technique of splitting in intervals in half, I know this is like randomized in some sense, but it's very reminiscent of this multi-level Monte Carlo technique that Mike Giles invented in, 2008. So I wonder if there's some kind of connection between your techniques and multi-level Monte Carlo. So instead of trying to get a single sample from the end, you want to estimate some expectation of the stationary distribution, say. Is there some connection at all, or maybe not?
This I'm not sure. I'd have to think about this. Yeah. Thank you.
Precisely in this slide, you're having the graph bounded by the two quantities. If you're thinking of a scheme where you have heavy tails and you don't have exponential of minus something, but you have something 1 over some potential instead, have you tried to implement this and try to get a sample for something with polynomial tails, for instance?
Yeah, so my advisor, Murat, has a paper on this. We haven't, like, as far as I know, there's no like midpoint for this, but Murat, who's like right behind you, should have some ability to comment on like, yeah, I believe that was for like Euler schemes, so I don't really know what happens for randomized midpoint. As far as I know, nobody's done this analysis. I'd expect it could do better, but these things, you have to do a bit of legwork to actually get the rate, so I couldn't tell you like specifically what type of rate you would get and what improvement you get over like Euler scheme.
Yes,
Yeah.
I wasn't thinking on Euler. I was thinking exactly on this one. Like with
Yeah. No, we haven't like done the analysis. I'm sure you could try to implement it practically. I don't think it would be very difficult. Yeah.
Okay, maybe we can take any further questions offline. So let's thank Matthew again, and we'll see you again tomorrow.
Thank you.